Hi, my name is Michael Way, and today I'm here to talk to you about C2000's new Concerto MCUs. Concerto is unique in many ways, and we'll talk about what these aspects are and how they can help to eliminate compromises in your designs. This is the agenda, and we'll start with an overview of what challenges exist today and how Concerto addresses them. Then we'll take a look at TI's MCU portfolio and how C2000 and Concerto fits in. We'll then dive into more details about Concerto's features and architecture. Finally, we'll end by showing you some of the software and tools that TI provides to make development and programming easy as you rein in the capabilities of Concerto. Digital control is bringing new possibilities in driving smarter and more efficient systems. Connectivity is becoming pervasive in applications that previously didn't require communication. Today, in many real-time control applications such as automation or energy conversion, one of the biggest compromises is finding a balance between robust loop control and adding communications or host functionality. But what if you could eliminate some of those compromises? In the past, there were two solutions to this problem. The first, in cost-sensitive applications, was to select one MCU that would perform both control and communications functions. From a hardware standpoint, it's a simple solution, but often requires a compromise on features and performance. In addition, software becomes more difficult as tasks and interrupts must be prioritized properly. While this solution is very appropriate for deeply embedded systems, it requires sacrifices by way of features, performance, and possibly a complex prioritization system for tasks. A second solution is to use two microcontrollers, a host microcontroller taking care of communications, monitoring, and other system functions, while a second loop microcontroller focuses on the real-time control aspect. This solution provides clean partitioning but adds cost, complexity, and latency from communication between the two microcontrollers. But with C2000's Concerto family of microcontrollers, the need to compromise is eliminated. By combining an industry-leading host core along with an industry-leading control core, Concerto provides the best of both worlds in one device, simplifying both hardware and software aspects, all while reducing cost. You can see here the control and host portions. On the control side, we have the C2000 C28X core. With industry-leading computational performance, hardware acceleration for different functions, and floating point capability, is the best solution for real-time control applications. Along with the core are some of the peripherals that you've seen with previous C2000 devices, such as the high-resolution PWMs and the high-speed precision analog. Additionally, we've made some additional enhancements to these peripherals that we'll talk about later in this presentation. On the host side, you'll find the tremendously popular ARM Cortex-M3. With Concerto, you can dedicate this core to the system management and communications aspects of the application. There's a slew of communication peripherals connected to the M3 as well, including USB, Ethernet, and CAN. So, taking a step out again, Concerto provides independent and optimized subsystems on a single device. With Concerto, you're getting a single chip, single platform solution to make your designs easier, as well as tightly coupled interface for communication and reduced latency between the two sides. So what does this mean in a real system? Let's take a look at industrial drives and automation. A significant portion of the world's energy consumption is used by electric motors. Sheer volume contributes to this, but so does the fact that many of these motors are open-loop motors that run at full power 100% of the time. Adding intelligence and closed-loop control allows these motors to be controlled more efficiently, where it consumes only a fraction of the maximum power under light load conditions. But it's not just efficiently spinning the motor to save energy. A lot of our customers that make industrial drives and work with automation need real-time control so that they can get the precision that they need. There's a lot of custom software that goes into these algorithms. There's a lot of analysis when it comes to different aspects like state of health of the motor, position and speed, strength, for instance, how much force to exert in a robotic hand. All of that is the responsibility of the control side. These systems also need a great deal of task management if you have an operating system, or system management which takes in the inputs of other sensors and data from communication. Communication is also a huge part of these systems. First, it's needed for things like coordination of different motors in a system. Take a multi-jointed robotic arm, for example. An arm needs to be able to pick up and move an object with varying weights, which introduces all kinds of different loads on each motor. Communication between each of the motors is required to make these types of dynamic, precise movements. Beyond communication within the system, industrial drive and automation systems need high-speed connectivity, like Ethernet, to remote control centers. Another more pervasive technology that you and I use every day is servers and data centers. These consume a huge amount of energy, for which even a single percentage point of efficiency increase can save millions of dollars in electricity consumption. But increasing efficiency is not easy. Servers are complex systems with multiple power rails and multiple subsystems. For example, a server rack may need to be supplied with 5 volt, 12 volt, 24 volt, and 48 volt rails. Each of these rails needs to have clean, precise power to maximize reliability. This is where the C28X really shines. The math capabilities and precision peripherals lend themselves perfectly to these requirements. By being able to drive multiple rails independently, the C28X side of Concerto will be able to handle different loads on each of these rails and dynamically adjust each profile to maximize efficiency. However, that's only half of the story. There's also a need for system management, to balance the loads, to run diagnostics, to detect irregularities and quickly switch to UPS backup systems without skipping a beat. All of this information needs to be communicated back to a control center as well. The Cortex-M3 core can execute on every one of these aspects, ensuring that the C28X can focus on the power conversion. Another example is solar farms. Many of the advantages that we talked about in the previous applications also apply here. Efficiency is the name of the game for solar panels, and while much of that depends on the panel itself, there's much that can also be done on the controller side, including finding the voltage-current ratio that extracts the most amount of energy at any given intensity level in the panel, which is called maximum power point tracking. The C28X is particularly proficient at these algorithms. There are also multiple power conversion stages, and the control side is built to handle all of them in one package. You can start to see some of the significant advantages that Concerto brings to end applications. Any system that requires communication and any sort of real-time control can benefit hugely from Concerto. We talked about motor control and power conversion, and it extends to automotive, especially in hybrid and electric vehicles, e-metering and power line communication, LED lighting, and much, much more. Now that you know the benefits that Concerto brings, let's take a closer look at the device itself. Concerto is the latest product in the C2000 32-bit real-time MCU series from TI. C2000 is distinguished by the C28X core, which we mentioned in the earlier examples. Concerto itself actually borrows many features from the Piccolo family, as well as the Stellaris MCU family, so if you have previous designs with those products, you'll find it very familiar. If we take a high-level look at the applications that C2000 has been successful in, you'll see how Concerto fits well into the C2000 portfolio. We already talked about digital power, renewable energy, and digital motor control. LED lighting can be very complex, as requirements can be stringent to extend lifetime and to maintain color balance and intensity. C2000 has always been popular in automotive applications, such as power steering and radar sensing. In general, I think the trend you'll see is that all of these applications require precision sensing and control, and we see a wide range of applications that we can't fit into one slide. Coming back to Concerto, here's a block diagram of its features. You can see here that the device is nicely partitioned into two separate subsystems, one for real-time control and one for host communications. On the control side, we have the C28X core with floating point with all of the related control-oriented peripherals that are needed to execute complex algorithms that are needed for precise, efficient power conversion. The host subsystem, based on the Cortex-M3, features advanced connectivity peripherals for communications, including Ethernet, USB on the go, dual CAN, and multiple serial communication ports. You can see that both subsystems have dedicated flash memory up to 512 kilobytes so that developers can execute code separately off of each core in order to maximize performance of each subsystem. In some cases, customers will have separate software engineering teams to handle either the control side or the host side. Separate flash banks allow engineers to focus on their side and not be concerned with the amount of flash required by the other team. That said, Concerto also includes up to 64 kilobytes of shared RAM to give developers the flexibility to partition it to either subsystem according to their design needs. Customers who are heavy on the control side will likely choose to partition the RAM to the C28X core, while customers who need to do more communication can choose to dedicate more RAM to the Cortex-M3 side. Concerto also includes shared analog because safety is becoming more important in green applications, and this configuration allows each core to check inputs from the ADC. We'll talk more about safety a little later in this presentation. There are no special power or clocking requirements for Concerto, so it's just as friendly as the Piccolo power and clocking scheme. Basically, it has all the conveniences such as a single rail supply with an internal voltage regulator, internal oscillator, and clock fail detector. Let's take a deeper dive into Concerto's components. As we mentioned previously, Concerto's host subsystem is based on the Cortex-M3 core, which is a 32-bit machine. It features a Harvard architecture characterized by separate buses for instruction and data. The beauty of this system is that it is entirely C programmable, even for boot code and system configuration. Some of the best features of the Cortex-M3 processor includes integrated hardware support for interrupts through its nested interrupt controller, NVIC, to deliver industry-leading interrupt performance, and the memory protection unit for system reliability and to catch prohibited memory location accesses. The control engine is based on the C28X plus floating point processor, which supports IEEE single precision 754 floating point operations. Native floating point brings many advantages, not only performance-wise. Floating point is more robust, meaning it is less error-prone than fixed point math. It can also do the same math operations or functions as fixed point with significantly fewer instructions, resulting in easier development and faster time to market. Engineers usually start development in floating point, then translate the code into fixed point before implementing them in their final designs. Eliminating the need for this conversion reduces development time as well as prevents most scaling and saturation issues. Through benchmarks against other C28X processors, floating point instructions help reduce the cycle count for math functions by 52%. Double precision operations will require support libraries. No changes have been made to the C28X plus FPU base set of instructions, pipeline, or memory architecture for Concerto. Therefore, programs written in processors like Delfino and Piccolo are completely compatible with Concerto. The Viterbi CRC and Complex Arithmetic Unit, or VCU, enhances the digital signal processing capability of the C28X CPU core. By adding additional hardware processing for Viterbi encode and decode, cyclic redundancy checking, and complex math operations, the VCU can increase processing speed by up to 7 times in math-intensive applications, especially power line communication. Although the ADC, the comparator, and the temperature sensors are not part of the control subsystem, they can be accessed through the CIB, or the Common Interface Bus. The Enhanced Pulse Width Modulator peripheral is a key element in controlling many of the power electronic systems found in both commercial and industrial equipment. An effective PWM peripheral must be able to generate complex pulse width waveforms with minimal CPU overhead and intervention. It needs to be highly programmable and very flexible while being easy to understand and use. And that's exactly what C2000's PWMs were designed for. Concerto's ePWM modules are very similar to Piccolo's PWMs, so if you've worked with them before, you'll find it very familiar. Just to recap, each PWM module has a dedicated 16-bit time base and supports 2 PWM outputs. The time base module contains logic for synchronizing with subsequent or preceding ePWM modules as well. It then passes on the time information to the counter compare module and the action qualifier module. The counter compare handles all of the compares to capture events, eliminating the need for extensive CPU interruption for PWM generation. It catches events and passes it on to the action qualifier. The action qualifier makes it even easier on the CPU because it can be programmed to automatically react to any event sent from the counter compare or interrupt and set the PWM output accordingly. This is essentially how the ePWM module works. It also includes extra portions for additional features such as programmable high-resolution deadband generator, PWM chopper, trip zone generator, and perhaps one of the most unique aspects of this PWM is the high-resolution PWM output, which we'll talk about on the next slide. New to Concerto is the high-resolution deadband and phase shift, as well as new compare events to enable more precise waveforms. This high-resolution module is what enables the unparalleled resolution in Concerto's PWMs, which is on the order of 150 picoseconds. On our competitors' devices, the step size is 15 to 25 nanoseconds, just for comparison. You can see here that with the high-resolution module, you have much greater precision on when the edges can switch, so you can have this resolution on both the duty cycle and frequency. And again, this is augmented by the high-resolution deadband and phase shift to make the most capable PWM outputs on the market. The ADC is also very similar to Piccolo's ADC. It's a start of conversion based ADC, which allows for easy creation of conversion sequences that can be mapped to specific start of conversion triggers. Triggers can come from software, PWMs, GPIOs, or CPU timers. Again, Piccolo users today will find it very similar to switch to Concerto. The unique factor is that Concerto contains 2 full ADCs along with 6 analog comparators. These 2 ADCs run independently but share channels and triggers. You can see here that both the M3 and the C28X can access the ADC as well as their respective DMA buses. So you know that there are 2 cores on this device. You know that they have dedicated memory, and you've heard how I mentioned that having them both on one die eliminates the latency associated with 2-chip solutions. You're probably wondering how they communicate. We've added an interprocessor communication structure, or IPC, on this device. There are 3 ways that you can use the IPC. The basic option is a very simple measure that does not require any drivers. This option only requires the IPC registers to implement very simple flagging of messages passed between the processors. The next step up are the IPC drivers. Some applications need more structured, driver-based functions for reading or writing data, setting and clearing bits, and function calls. TI actually provides 2 sets of drivers, IPC Lite and the main IPC API driver. As indicated by the title, IPC Lite provides the essentials while focusing on ease of use. So it only uses the IPC registers and doesn't use memory. It can only handle 1 interrupt and 1 message at a time. The complete API driver library allows much more. It builds circular buffers in RAM, and you can queue up to 4 messages, and it can also handle multiple flags at one time as well. The last option is via DSP BIOS or SysBIOS. SysBIOS version 6 will provide a new transport module that will work with the shared memory and IPC resources on Concerto. We mentioned safety earlier in this presentation. A clear trend in greener technologies is that more and more microcontroller safety features are required in applications such as industrial drives, hybrid and electric vehicles, wind turbines, and solar inverters. This not only allows for greener applications, but safer applications as well. Safety in applications such as hybrid and electric vehicles are obvious in that lives need to be protected in case of a failure with the vehicles. However, industrial drives, wind turbines, and solar inverters are not as obvious in terms of needed failure protection. These applications need a certain level of safety as well, in that high voltages drive these applications and a failure can be catastrophic. We categorize the safety features on Concerto MCUs into 3 main buckets. The first is error detection and correction. The second is redundancy of functions, and the third is security. When it comes to error detection and correction, special features are needed to detect and correct a fault. For instance, ECC is needed on memory. This allows errors to be detected and then corrected in both flash and RAM memory. We also have parity, which detects errors on special peripherals and registers. CRC is a checksum algorithm run on memory to detect errors as well. To help with system-level detection, comparators have been placed on chip in order to detect overcurrent and overvoltage conditions. Redundancy for functions can add an extra level of detection for critical IP, but the implementation is different for various customer systems. Redundancy is different from error detection in that the designer must take advantage of the redundant features to make the system more robust. For instance, the 2 cores and 2 ADCs in Concerto MCUs are available for a customer to use to make sure the application code is running as intended. This could be used in a motor control application where the Cortex-M3 could run a motor calculation while the C2000 core can do the same calculation. The result can be checked to see if they come with the same answer. There are 2 clocks so that if one clock has a fault, the secondary clock can serve as a backup. Security is on this device to help customers protect against tampering with the system. Locked protection on GPIO registers allows for the registers not to be overwritten during runtime. Memory protection is available so that customers can securely lock their code. Concerto is unique because we provide 2 code security lock zones so that both a third party and the customer can lock their code. We also allow customers to permanently disable the JTAG so no one can try to access via JTAG and read the internal code. The multiple safety features on Concerto MCUs will help customers protect against faults and failures in a system as well as protect important IP. Here's an overview of the configurations offered in Concerto. You'll see that we really only varied the CPU speed and memory sizes between these configurations, with USB and Ethernet as an option. We start with the entry level, as signified by the E in the part number, which features a 60 MHz Cortex-M3 and a 60 MHz C2000X. The mid-level, over here, bumps the speed up to 75 MHz per core. For high level, these devices are actually capable of 2 different settings. It can run both at 100 MHz each, or there's the option to boost the C2000X speed up to 150 MHz. However, this will require the Cortex-M3 to be clocked down to a maximum of 75 MHz. And this is purely because of the clocking setup. This is decided by the customer when they initialize the device, that's why it's the same part number. Another variant to point out is the 768K of flash. In all the other configurations, flash is divided 50-50 between the 2 cores. So 256K per core in these devices and 512 KB per core in these devices. In the 768 KB configurations, it's still the base 256 KB per core. Then there's the extra 256 KB that goes to the M3 core on connectivity devices, which are the ones with USB and Internet, and it goes to the C2000X core on base devices, the ones without USB and Internet. This way, connectivity devices can get more flash for the Ethernet and USB stacks, while the base devices can focus more on the algorithms that are run on the C2000X core. The extra 64 KB of RAM, however, that varies between these devices, are split into masterable blocks, so these are much more flexible. Okay, we've gone over the devices and what it's capable of, so the next step is to show you how we can help you get started. Luckily, we've got some great software and hardware tools that will help you hit the ground running. We at C2000 have spent a lot of time trying to make sure that customers can easily and fully leverage all of the features that our devices. We at C2000 have spent a lot of time trying to make sure that customers can easily and fully leverage all of the features of our devices and the breadth of system application knowledge that TI has built over the last 15 years. That's why we've created controlSUITE, which is a portal for all software, documentation, support, automatic upgrades, and more. When you download controlSUITE, all of the kit and device software is installed on your computer, and the controlSUITE interface helps to navigate through those resources. Here's a snapshot of the controlSUITE interface. On the left side, you have the main navigation. The core files are all under this section. When you click on the devices, you'll find all device-related drivers, header files, and documentation. The kit section contains all of the kit software, hardware files, and documentation for the development kits we offer. When you click on it, you'll see everything here on the right. You'll see a list of all of the kits, and when you click on that, you'll find a description as well as all of the resources. So there's example projects, there's documentation, there's online resources, and more. An important thing to note is that controlSUITE contains all of the hardware files for kits. This means the bill of materials, the schematics, layout, Gerber files, everything you need to recreate the kit. And that's because our kits are designed in a way that is modular for easy modification or for you to pull into your designs. We also have libraries, such as DSP math libraries, application libraries for motor control and digital power, and much more, all arranged in the same fashion. There's even more to the controlSUITE interface as well. The update feature keeps you up to date so that you know when we push out another release. You can also access datasheets and application notes. We have all of our free online training as well as hands-on courses listed, and the list goes on. I also want to mention TI's E2E forums, which can be found at e2e.ti.com. We have all of our engineers along with a fantastic community to help answer any questions and solve problems. It's been immensely helpful to many customers, and you can catch a glimpse of some of the latest C2000 posts from the training tab here as well. If you're not already familiar with C2000 tools, most of our tools are built on the control card platform. Control cards are little cards, if you may, that contain the device and all the support circuitry. Everything that's related to the device is contained on this control card in a standard form factor, which is based off of the DIM100 socket. This card then plugs into all of our evaluation and application kits. This way, you have a standard card that you can unplug to test different devices. Also, if you happen to blow the chip, you can just replace this one card instead of the whole application kit. Concerto builds upon this, and we have the Concerto H52C1 experimenter kit here. It's got a control card and a baseboard that brings out all of the pins along with the prototyping area. We also offer the control card by itself to those of you who already have a baseboard you want to use. And this control card has a ton of features on it. The USB JTAG emulation is on there. There's an Ethernet port, micro SD slot, and a micro USB port as well. Just as we designed the Concerto hardware into two optimized subsystems, we also portioned the software and programming environment into control and host sides to ease design. To help our customers differentiate their products, we provide the needed software components as well, so that customers can leverage the 15+ years of TI software experience. Programming Concerto is like programming two separate chips with a single Code Composer version 4 integrated development environment. A programmer can easily switch between coding the real-time control side or the host communication side of Concerto. If there are two software engineers, then each respective software engineer can just focus on whichever partition they are the expert on. Thanks for participating. Hopefully you're excited about Concerto and the possibilities it brings. It's a huge step forward in three major ways. One, it allows efficiently partitioned designs and reduces complexity. Two, it has tons of safety features to help improve the safety of your system. And three, Concerto, along with TI's development tools, helps you to easily scale designs and focus on differentiation.